So this continues a problem that we started in the previous video, where we're looking at these two blocks, let me show you that are being pushed across the floor by a 300 Newton force. And in part B it asks, what is the force that this block applies on that? Or, since the third law says it's the same, what's the force that the 1.2 kilogram block applies to the 0.6 kilogram block? Well, because we now have the acceleration, we can simply take our result right here and substitute it back into this equation and solve for N3. And that's what I plan to do. So you can see that when I do this, I'm going to have N3 minus mu mbg times mb, and now I'm going to put in the force here, so I got force over ma plus mb minus mu mbg. Notice I didn't put in numbers again. Numbers tend to obscure what you're trying to understand about a problem, and they can often also put in these rounding effects. For instance, notice that the friction force by the second block in this particular problem cancels out in the thing. It has nothing to do with the nature of the force between the two blocks. You would get a similar force even if they had been sliding across a frictionless surface. If you're plugging in numbers, you do not get these sort of insights. So, solving this, what you find is that the force that's needed to be applied between the two blocks is the fraction of the second block's mass that's not getting the force applied to it from the external object, the 300 Newton force, divided by the total mass of the system. All of that times that external force. So N3 would be equal to 0.6 kilograms over 1.8 kilograms times 300 newtons. Well, this is 1/3 times 300 gives a force of 100 newtons. So that's the force, 100 newtons, between the two blocks. And like I said, it's completely independent. It would be the same answer regardless of the coefficient of friction between the blocks and the surface they're sliding on, even if in fact they were frictionless. Alright, that finishes this particular example.